Hello, in this video we are going to see the main approaches to solve indifferent curves and budget constraint. And for one of the approaches we are going to use the concept of gradient. So very intuitively, if you have a function that depends on these two variables, and if you want to calculate the gradient in this point, then the gradient is a vector here that points to the direction that you have to take if you want to climb this mountain following the maximum slope. So if in each point you want to calculate the maximum slope, then you follow the gradient, and then you can reach the top following the direction of the gradient. This is a method to find local maximum. So if you want to calculate the gradient in this point, then you see in which direction you get the maximum slope, and then this is going to be the gradient in this point. If you want to calculate the gradient in this point, then you go up, you see in which direction you get the maximum slope, and then this is going to be the gradient. So now we come back to the previous video, and then we found that here is the optimum. So if you evaluate the function here, you get the maximum utility subjected to this constraint. So in this example, this is the gradient, this black line, and you see that it points in this corner because here you see that the maximum slope that you get is following this direction. If you want to calculate formally this gradient, what you have to do is to calculate the partial derivative with respect to one variable and respect to the other variable. But very intuitively, if you take one as constant and you move the other variable, then you get not a surface but a curve, which is this curve, and then you take the derivative in one dimension for one variable and for the other variable, which very intuitively tells you how it grows in one direction and how it grows in the other direction. Well, formally the derivative is this divided by this, but we are going to take this value multiplied by 10, so we're going to take this blue segment as one partial derivative, which is this blue segment, which here is 5 divided by 2 is 2.5, which is this 2.5, and then this 2.5, the red part, is this 2.5, the red part. And here the partial derivatives are the same because the function is symmetric. So here we are taking the particular case that the prices are 1 and these exponents are the same. So if you take the gradient in this point, and in this point, and in this point, and in this point, you see that in all of the cases point toward this corner because it's where you get the maximum slope. Formally, you can prove that it's always perpendicular to the tangent in this point, to the tangent of this yellow indifferent curve. But the important point here is that there's only one gradient, which is this one, which is perpendicular to the magenta line that represents the budget constraint. Now, if we focus on the budget constraint, so now we are going to take this variable, the printer, as a good 1 and the cutter as a good 2, G1 and G2, and then this budget constraint, this we can write this, and then we can write a function that depends on two variables in such a way that this can grow, not necessarily to equal to 0, but a function that depends on these two variables. So if we calculate the gradient of this function, which by definition is the partial derivative with respect to one variable and the partial derivative with respect to the other variable, so it's this vector. So formally, the partial derivative of this function with respect to g1 is just the derivative of g1, which is 1, and similar, the partial derivative with respect to g2 is also 1, because this is the only variables that vary for this case. So the gradient is in all of the cases 1, 1. In all of the cases is 1, 1, which is intuitively, because if this function grows, it's like we increase this value, then you get a parallel shift in that direction, perpendicular. So that's why in every point the gradient goes in that direction, because it is the growing direction of this function. But there is only one point in which the gradient of this function c has the same direction of the gradient of the utility curve. And you can see that the gradient now, the gradient of this blue indifferent curve is perpendicular, so this is the gradient. So you see that the direction of the gradient of the utility curve is different of the gradient of this function c. And this point satisfies this constraint because it is within the magenta line, but the utility in this point is, you follow here, you see the label 2 is 2, where this one is 2.5. And the utility in this point that also is within the magenta line, you see that belong to this indifferent curve, and the label is 1. So here the utility is 1, here the utility is 2, and here the utility is 2.5. So here you have again that the gradient have different direction. So in this point both gradient have exactly the same direction, and this is the key point that the Lagange method use. We are going to see the Lagange method with much more detail later with numerical examples, but roughly speaking, what you do is to build a function, L is for Lagrange, that you have the utility function minus lambda, that soon we are going to see what this lambda represent, and then this c, which is this c that depends of these two variables. So what you do is to take the partial derivative of this L respect to g1, the first variable, and equal to 0, then respect to g2 equal to 0, and then you take the sorry, here is c, you take the partial derivative respect to lambda, which is going to give you c equals 0. And then you solve 3 equations with 3 unknown, which is the value of lambda, c1 and c2, and then you get the optimal solution. But if you want to prove this, what you use is this concept, because if you say that in this point the gradient of the utility has the same direction of the gradient of this function c, so let's say is, for example, 3 times this vector is 3 times this, for example, in this case lambda would be 3, and then the gradient by definition is the partial respect to g1 and the partial derivative of utility respect to g2, and the same for c, partial partial. So you get that the first component, this is equal to lambda c g1, and u2 g2 is lambda c g2. So you get this expression out of the concept that both go in the same direction. And this thing, if you take this thing here, this is exactly this. So actually this thing is what you need to prove the Lagange method, because in this example it's quite intuitive to find out that the solution is 5, 5, because both prices are 1 and because this is symmetrical. But if you have, for example, that the price of the printer is not 1 but 2 million, so you will see that this point moves here, because with a budget of 10 million you will be able to buy not 10 but only 5 printer, because the price is 2. And then if with you have here one half, then this is symmetrical. But if you have, let's say, 0.7, then this is not going to be symmetrical, and then the side of the printer will grow faster than this other side. So this function is going to be like this. So here this side grows faster, and then if you see this from above, then you will get this. And then if you take a picture of the base of this parallelepiped, then remember that this will go here, so this is going to be the magenta line that represents the Lagange constraint. Okay, in the next video you are going to see a simulation of this, and then you will get a very intuitive idea that will help to understand the following videos. Okay, that's it. Thanks for watching, and see you in the next video.